much more details this morning and what Aleh did on dynamic envelope theorems. So this should be relatively easy for you, I think, to understand after these two presentations. So it's joint work with Mike Golosov and Max Troshkin. Okay. So if you think about classic public finance, so one of the key questions is how to efficiently redistribute among individuals or how to provide social insurance. It's easy to do if everything is observable. It's difficult to do when some types are unobservable. So in addition to this redistribution of social insurance, you will be running into the problems of incentives. So it's always a trade-off between insurance and incentives. So the starting point, I think, of all of this, of answering this question in a static framework is done by Jim Mirrlees. So it's the way how to write down this problem, the way how to resolve the trade-off between insurance and incentives is more or less done by Jim Mirrlees and I think quite significantly extended by Emmanuel Seitz and by Peter Diamond in better understanding of what Mirrlees implies. However, if you think about many of the questions that have been talked about in this school, some of the questions of public finance are inherently dynamic. So, for example, how should one tax capital income? How should one tax labor income over time? Should the labor income when you're older be taxed differently from labor income when you're younger? How should consumption be taxed? How to tax bequest? How to tax or subsidize education? How to design social insurance? All these questions are, at their heart, fundamentally dynamic. They deal with redistribution or insurance of stuff that can happen tomorrow, stuff that can happen today, the trade-offs between insurance and incentives today and tomorrow. So for this, you need to have dynamic approach. So the dynamic approach that have been quite successful, I think, working on this issue is the new dynamic public finance. And many people have worked on this issue, including Emmanuel, myself, Mike, and Max, the co-authors of this paper. So this approach is, I think, to some extent comparable to the static Mirrlees approach as it was done, say, before Peter Diamond or Emmanuel Seitz, is that it provides a conceptual framework, or more theoretical maybe framework, how to think about these issues. And still, despite many of the papers written on this topic, the question, I think, still remains, or remained until quite recently, is what do these models imply about designing taxes or social insurance schemes on the models which are brought closer to the data and can potentially provide practical implications. So how to design optimal dynamic taxes. Okay, so what we're going to do in this paper is the following. So we're going to look at a model which is going to be quite similar to any of the life cycle models that I have looked at or have seen in modern macro. And the key contribution that allows us to make progress in solving these models is the use of first-order approach, actually developed by Aleh and co-authors and developed by Marek Kapichka for these dynamic applications. So before, the only things we could really solve were either very limited, very special circumstances, like, for example, disability insurance scheme, which we're going to be talking about next time, where types are fully persistent, they're stochastic, but once you say become disabled, you stay disabled forever. Or IID shocks, or maybe some other limited examples. What first-order approach gives you? First-order approach gives you a very nice recursive formulation to write this problem in a manageable form that is amenable to the analysis, and that is also can be solved on a computer and brought together for models which are not just very special cases of general shocks. So the second thing I'm going to do is exploiting this first-order approach. I'm going to think about how dynamic model is different from the static model. So if you looked at some of the literature here on dynamic public finance, often many people have a feeling that, well, it's very theoretical, it's very, very different from classic public finance. So even if you know quite well the classic static Merleesian taxation, you still would be somewhat puzzled about how dynamics, because the tools and techniques seem so different there, how it would relate to the classic public finance, static public finance applications. And here I'm going to rewrite them all recursively. And what does recursivity help me? And I think that's, to some extent, I think a point of most of the modern recursive macro is that recursive formulation essentially breaks down the model into a two-period model, which deals with today and tomorrow. And once I have this, this characterization, I can think about the model written in a proper form as a model with two goods. One good is today's good, say consumption and labor. And the second good is properly defined promises and the utility of a promise over the resources the planner wants to allocate for tomorrow. And by writing the Bellman equation this way, and by thinking about the dynamic model as a static model with two goods, today's goods and tomorrow's goods, I think one can a little bit demystify the optimal dynamic taxation and bring it closer to the classic public finance applications. What I'm going to do is also, I'm going to look and find the key parameters to calibrate these models from the US microdata, and I'm going to compute the optimal distortions. Just want to notice and mention quite prominently the paper by Ivan and Emmanuel, which Emmanuel is going to be talking tomorrow, which is quite related to what we do and does a similar exercise in continuous time and gets much more traction on many of the issues related to the intertemporal provision of incentives. And I'll compare, actually, some of the results here, and I build on some of the results that they do here, and I'll mention this. OK. So what's going to be the main conclusion of this paper? So there are going to be, I guess, three main conclusions. The first one is that dynamic distortions are going to be quite different from those you would get if you, say, built your policy recommendations based on static optimal taxation exercises. So one of the key things that comes out of the static Merleesian models, for example, from papers by Diamond or Seitz or Piketty, is that if you have unbounded distribution of types with a pareto tail, with a fat tail, then what you want to have is, for this very high incomes, you want to have labor taxes or income taxes increasing, and they can actually reach quite a large number, say 50 to 75% for a reasonable calibration. So, if you based your policy on the static exercise, you would say, well, we should tax the high-income guys or high-skill guys quite prominently. We should tax them at 50 to 75%. I'm going to show you that in a dynamic setting, the conclusion about the asymptotic labor tax on the very high or the very high incomes on very high skills is going to be quite different. So the labor distortions are going to be quite small, and asymptotically, they're going to go to zero. Instead, what you would want to do is you want to substitute capital distortions for the labor distortions. I'm going to provide you intuition for this. The second main conclusion is that the optimal labor distortions are going to be age and history dependent. So specifically, I'm going to show you that it's optimal, or there is a force driving the labor income distortions lower in the earlier periods of life of an agent. And you'll also see how it plays out quantitatively. The second thing, which is quite important, is that conditional distribution, conditional on the incomes you got, they shift up with the incomes you have. So it's about the conditional and about age distribution of skills. So finally, I'm going to compare the welfare gains from nonlinear optimal taxation to the optimal linear labor distortions, and I'm going to conclude that they depend on the degree of redistribution that the planner wants to have. Okay. So let's start with an environment. So I'm going to look at a model where there are t periods, and t is going to be finite. Actually, easy.
I was just to go back in terms of the motivation. My understanding is for the static stuff, for dynamic settings, my understanding is our confidence interval for what the elasticities are pretty big. And I know David Card has a intertemporal, or he has a paper reviewing all the intertemporal literature, and he basically concludes he's not that confident about what we know. And so conclusions from a setting where you have some parameter you want to plug in calibrations, aren't they pretty wide in terms of confidence intervals?
So I mean, yes and no. So I'm going to show you how in the static setting, there are two actually key forces that determine the size of the labor income tax. One is elasticity, which you say. The second is the tail ratio. So how many people are above you versus how many people are below you. So for and you can play with this, but I think for reasonable estimates, you would still get quite large. Even if you stick the static, or your favorite dynamic elasticity, I should probably actually do it, then you still would want to have a high income tax on the high tax on the high income people. Okay? And you want to have zero income tax in the dynamic setting. All right, so T finite, I can do T infinite. Actually, it's easier in some dimensions. I'm going to have preferences over consumption and labor and discount factor beta. I'm going to have a continuum of types theta t. There's going to be some initial distribution from which they are drawn. I'm going to call it f of theta. And then the types are going to evolve stochastically over time. And your type today is going to depend on the type yesterday. And there's going to be an age-dependent probability distribution of the types. Okay, so agent learns their type, or his or her type today, but not before today. Obviously observes the whole history. If you have a type who supplies theta t, who has skill theta t, supplies L of theta t units of effort, then the type produces theta t times LT of theta t units of output. Consumption and output are observable, but neither your skill nor your effort are observable. I'm going to have a partial equilibrium exercise. I'm going to, in fact, assume that you can transfer resources across periods with the rate delta to the power minus 1. And actually, I'm going to assume for some of the things I do, delta is equal to, delta beta equal to 1. Okay. All right, so let me write down the Planner's problem. So the Planner's problem, on one hand, it looks complicated. On one hand, it still fits on one slide. But I think the devil is in the details. So what does the Planner do? Well, the Planner maximizes over all consumption and effective labor allocation C and Y over the whole life of an agent. And maximize here, I'm just going to have a utilitarian Planner, maximizes the expectation over your utility of discount utility of consumption and labor, given your skill. Subject to feasibility constraint, whatever is produced in the economy, discounted by delta, the marginal rate transformation across periods, is less than what is produced, exactly the same present value. Well, then, I guess the interesting part is this incentive compatibility constraint. It looks, again, deceptively simple, but obviously that's where all the meat is here. And it says that if I tell the truth, then this should be better than any possible sequence of deviations I can have. Okay? Well, obviously, this last part is very complicated, and here just written in a general form. All right, what I'm going to be looking at, I'm going to be looking at three objects. The first object is going to be a labor distortion. It's a difference between the marginal utility of consumption and the marginal utility or disutility of labor. Okay. I'm going to have a savings distortion, which is the intertemporal distortion. I'm going to call it by tau Ts. I'm also going to have a lifetime saving distortion, which is the distortion between marginal utility of consumption today and expected marginal utility of consumption at the last period, which I'm going to assume that agents retired. Did I say this actually? So somehow I skipped the slide. So let me talk a little bit about this slide. Okay, so what other assumptions I have here? Well, I have preferences that are quite nice. There's single crossing property, concavity, differentiability. But also, importantly, I'm going to assume that consumption and leisure are complements, or consumption and labor are substitutes. Also have the free elasticity is bounded from 0. I'm going to have the following assumptions on shocks, on the distribution of the shocks. Again, I'm going to assume nice differentiability. I'm going to assume the boundedness of the tail ratio. And I'm going to assume another property, which I'm going to use for some of the results, or quite a few of the results, is that this property that guarantees a certain amount of persistence in agents types. So how to think about this? Suppose you have some previous type, theta h or theta l, then the probability, the relative probability of getting a shock theta, conditional on theta h and theta l, is decreasing with theta. Okay, and I'm gonna give you a little bit more intuition about where it's going to exactly play out. And I'm going to have retirement. So in the last period, in the period theta t, everybody has skill equal to 0.
Why are you putting a condition on the skill, which means that somehow you're limiting the process which defines the skill? Why not leave the process as is and then just time t decide that no one's working anymore?
So here, I guess they're going to exogenously stop working.
Because you're having effect now on all
Oh, for sure.
possible process could have evolved until now. When you say retirement, you're not retiring necessarily because your skills are diminished, but because you're at the age where you want to retire.
I could do that. I mean, this is going to be important for one result. I don't have to do it. I don't have to retire everybody. And for something, it's going to be useful for me. So in fact, something I'm going to show you tomorrow, the stuff I have done on disability insurance, there will be something which looks like endogenous retirement. People are going to be, given the profile of the skills, they're going to reduce the amount of labor they're going to provide as they reach 65 or 75 years. Okay. All right. So how does one do recursive formulation? So I'm going to talk a little bit about the general way how to do it. So there is a solution which always works, which is to do what Fernandez and Fallon did, is essentially they say the following. So let's introduce a promised utility / thread keeping utility, which is a function of your type theta prime yesterday and your type today. And it promises utility for a type theta prime who reports theta today. Okay? So you can write incentive compatibility constraint recursively in this way. So what does it say? It says utility of consumption and labor plus the promised utility if you tell the truth should be larger than if you say that you're a different type, theta prime, while the true type is theta, and you get a different promised utility given that you lie. This should be done for all thetas and all theta primes. Okay, you can write Bellman equation for this, but it's not very convenient. It's a very big object. So think, for example, about the IID case. In the IID case, the only number you have to keep track, not the function. The number you have to keep track is the promised utility. So here, you need to keep track of the promised utility plus the utilities for each of the agent as if, for all of the previous types, you'll have to allocate utility. You'll have to allocate the promised utility. So it's a much bigger multi-dimensional, or it's much bigger vector. Okay, so let me talk about how Fernandez and Fallon write recursively, and then I'm going to simplify the recursive formulation using the envelope theorems. Okay, so let me start with the problem t equal to 1. It's the easiest part. So while in t equal to 1, there is promised utility v. There was nothing. There was no types before. There was no type relation before. And this is the utility of consumption you get today plus the promised utility. And this is your probability distribution of each different type. Well, let's look at the incentive compatibility from tomorrow on, or from today on. It's the utility of consumption effective labor today plus, again, the truth-telling utility. But that on the right-hand side, I need to ensure that if I lie, what I'm allocated is worse than what I get if I tell the truth. And here I'm going to write it in terms of the cost minimization, the minimization of the resources. This is the amount of stuff that is spent on providing insurance today or distribution today, and this is the cost from tomorrow on. Okay, and again, we have to keep track the whole function omega of theta here. All right, so this is sort of easy for now. Well, let's see what happens in t minus 1. Well, in t minus 1, it actually becomes a little bit more complicated. Again, we have the same resource minimization problem. So first of all, it has the conditional probabilities here. So you have to condition on the previous type because it governs the evolution of the types. We need to have, again, the incentive compatibility constraint. But now, instead of just having one promised utility, we need to have the promised utility for all the possible types which were there yesterday. Let me just give you intuition for this. Why do we need to keep track of all the previous, why do we need to assign a utility for each of the previous types that could have happened? So in the ID case, obviously you don't need to do it. So what's the difference between the ID case and the case of the persistent shocks? If an agent were to lie yesterday, not only he lied yesterday, that's the same thing that would happen in the ID, but he also has an informational advantage over the planner because he knows his true distribution of the types while the planner, quote unquote, thinks that he still, he is the type that he reported. So what the planner needs to do, so now when you come to to the current period, the planner needs to ensure that when he gives the following today plus tomorrow allocation of utility, that no matter what your type was yesterday, you will, so I'll need to ensure that I provide the threat keeping, I provide the incentives not to report the wrong type yesterday. And this exactly is done by all of these threat keeping constraints. That is for all of the theta hat, which are not equal to theta. Again, so this is nice, but you can't really put it on the computer. You can't really do much with it. So I think an important step forward, which allowed for many of these things to significantly move forward, is exactly what Ilya was talking so far, and what Marek Kapichka as well did, is to apply envelope theorems, dynamic envelope theorems, to significantly reduce the dimensionality of the recursive problem. So intuitively, what it says is the following. So let's have now only two state variables. One state variable is the same thing as we have seen in many of the incentive problems, is the promised utility if you were to tell the truth. Okay. The second thing is the derivative of the promised utility function with respect to the previous period shock. So think about this intuitively as if an agent were to locally deviate yesterday, by how much should his promised utility change? So Ilya talked about sufficient conditions here. So it's actually relatively easy to write down the sufficient conditions for this first-order approach to be necessary. And it has only three things. So it has the monotonicity of the consumption with respect to skill. It has the monotonicity of the promised utility. And it has the monotonicity of this derivative of the promised utility with respect now to the first variable. So I don't know the answer how it's all related to the impulses that Ilya. Yeah. But yeah, but it's it'll be nice to see how it all relates. I mean, obviously it's not conditional on the primitives. However, it's again, so I'm a practical guy. So what I want to have is I want to solve this problem. I can actually solve in the relaxant problem. I can then just brute force it. I can check whether there are global deviations. That's possible to do. Or I can alternatively use these conditions to also check and to ensure whether my solution for which I solved the relaxed problem is indeed the sufficient condition. Okay?
Is there any hope of trying to relate those conditions to primitives? I mean, the first two look relatively mild regularity assumptions, that consumption is growing as a function of your report and that your consumption is growing. The second looks a bit harder, but is there like any hope of trying to...
I think Ilya provide us hope. So
well, we do solve the different simulation problem. In our problem, we have sufficient conditions.
true.
To ensure the sigma and the instance, because we solve a different problem, we don't know if it's harder.
Yeah. So I don't know the answer. I think it's a very interesting question, even to understand how this sufficient conditional recursive formulation relates to what Ilya was talking about in terms of the conditions on the primitives. However, it's for me again. So as I said, for practical applications, it's reasonably easy to apply these conditions. All right. So now let me do the recursive formulation. So this is a little typo. There should be hats here. So now my recursive problem became much easier. So in time t, I need to keep track only of 3 state variables: the promised utility on the path, the derivative of the promised utility, and the previous skill. Okay, so what do? I minimize the amount of resources spent today, plus the resources spent for tomorrow. This is the conditional probability. And I have a couple of other things. So first of all, I have the dynamic envelope condition written here. So in contrast to the static or to the ID case, it has this derivative, the W2 derivative. It has the definition of the lifetime utility. And it defines exactly what the utility on the promised utility on the path with which you come into the period, and the promised utility of the path for local deviation with which again you come into the period, and you can see here how this derivative is defined. Okay. All right. Let's stare for a second at this problem. So this problem seems sort of similar to the problems we have seen, like for example to the static model with 2 goods, however with one pesky difference. So exactly this utility W2, or the promised utility, the derivative of the promised utility W2. Well, I mean, what I'm going to do, I'm sorry for flipping it back. Let me again be a simple-minded guy. Let me load this thing here with the Lagrange multiplier associated with it. Okay, so now I'm going to have actually exactly very similar solution to the one with 2 goods, however, with a different objective function for the planner. And here, that's where my restriction on the stochastic process F2 over F would matter. If I have the Lagrange multiplier positive, then what this restriction would make the planner to be more redistributive to the agents of higher skill. So why is that? So let's just think for a second. I'm going to provide a little bit of intuition for this, and then we can just go on from this. So let's take an agent. Let's take 2 agents who have the same skill today. Let's look at the probability of the realization of the skill today. Suppose an agent yesterday just a little bit deviated downwards. So this assumption of the stochastic process says that the probability of an agent who deviates to the slower type of being the same type today, of being a particular type today, is lower than the probability of ending up of this particular type today if you didn't deviate. So putting this extra weight on in the objective function helps the planner to ensure that these deviations are not profitable. So to treat the agent such that this deviation are profitable, and by assuming this property on the stochastic process, I can actually I can rank the strength of this additional distortion that one has to provide to screen this potential line types. Okay, so now what I'm going to do is I'm going to assume a couple of things. So first of all, I'm going to assume that the discount factor is equal to the inverse of the marginal transformation. So beta delta is equal to 1. And I'm going to focus on the IID shock. So I'm going to talk about the persistence when it matters. Okay, so what I'm going to do now is I'm going to flip from the dual problem to the primal problem. So to do this, let me define another variable. Let me define the object ht of R, which is an indirect utility of an agent who has resources R in period t and gets optimal insurance from that time on. And this can be defined as just the inverse of the of this cost function of providing resources v minus 1. Okay? So now let's look at this dual problem. This dual problem is the following. Again, I'm going to look at this in the recursive format. Well, suppose you come in with the amount of resources R hat. So this is going to be your utility ht. And it's going to be the maximum over consumption and effective labor, the utility of this, plus the optimal utility from now on, given the amount of resources I move to the future. They're going to be an envelope condition, and they're going to be something that looks like a feasibility or the budget constraint like condition, where I have consumption today, resources that I move to the future, and amount of stuff I produced. Okay. All right, so the planner decides how to split the consumption between consumption today, between moving resource to the future, and how much to produce. Okay, so ht is the indirect utility of an agent from having R units of resources, assuming that the pattern of the optimal distortions holds from now on. So let's look at this problem. Is this problem that different from a static problem? Well, if we just kill this ht plus 1, it's going to be exactly the static problem with one good, the classic Merlisian problem. Well, but let's not kill this ht plus 1. Let's look at this. So we have utility of the good one, which is complementary with leisure, or at least weakly complementary with leisure, as I described, plus we have the utility of the future promises, which is separable from effective labor. So our model is exactly like the model with two goods, consumption today plus promises for the future. Okay, and I'm going to build intuition of how to think about the distortions here, exactly referring to the static Merlisian model with two goods. Well, let's again flip back to the theory of optimal commodity taxation. And what it says, if you have two goods, I want to tax the good which is more complementary with leisure. So why is that? Well, let's look at the deviation. Let's look at a very high skill agent pretending to be lower skill. What's going to be how is this agent going to differ from the truth-telling agent, from the lower type agent who works honestly and reveals his type? Well, the difference is that this deviating agent will have more leisure. Okay? And if consumption is complementary with leisure, that I want to tax, I want to distort that good more than this good R, which has utility H, which are the future promises. Okay? So I want to introduce a distortion if consumption and leisure are complements, or consumption and labor are substitutes. I want to impose a wedge between the marginal utility of consumption of the consumption good and between the marginal utility, or marginal indirect utility of moving R units of resources to the future in the incentive compatible way. Another way how to say it is that I want to tax good R more than I want to tax good C. Well, what if the cross partial is 0? Well, it means that I want to tax them exactly in the same way. I want to tax utility of the marginal consumption today as the indirect utility of moving R resources in the future. Okay? All right, so now we talked about inverse Euler equation. How is it all squares with that? Well, what's the marginal utility, marginal indirect utility of moving R units of resource in the future? I mean, as we have talked extensively today and yesterday, it's not equal to the marginal utility of the consumption tomorrow because exactly of incentive compatibility constraint. Okay? So, for example, because you have the incentive compatibility constraint, if you just move absolute resource to the future, it's not going to be incentive compatible. All right, so now let me think first about the case of separable preferences. So if I have separable preferences, the utility of consumption, the cross partial between consumption and labor and utility is equal to 0, then what do I get? So first, I get immediately that the marginal indirect utility of moving R units of resources to the future is exactly equal to the inverse of the expectation of the inverse of the marginal utility. So you have to do a little bit of work here, but I think Natalia, I know where she is now. So she asked yesterday how the inverse Euler. So why do you get 1 over u prime? So I guess this is a part of the answer for the separable case between consumption and labor, is that the indirect marginal utility of moving R units of the resource in the future is with the separable preferences exactly equal to this inverse. Okay? And immediately by noticing this, we get that with separable preferences, the inverse Euler equation. So inverse of the marginal utility of consumption today is equal to the expectation of the inverse of the marginal utility of consumption in the future. Okay? And exactly from this, by applying Jensen's inequality, you would get that the marginal utility, expected marginal utility of consumption in the future is higher than marginal utility of consumption today. Okay? All right, so what happens with non-separable preferences? Well, we can't really determine the sign between the expected marginal utility of consumption tomorrow and this indirect utility of moving R units to the future. Well, for preferences close to separable, one can show that the savings wedge is positive. But in general, you can't really do it. So there is no general result for an analog of the of the inverse Euler equation, or of the wedge at least. Just think about this. We will only have the result for separable preference.
What would it mean to be close to separable? You wrote that result that the saving wedge is positive.
I mean, you can again. So you can put I guess the sign of the cross partial if it's low enough, small enough, close to 0. For example, if you have the sign of the cross partial going in the limit to 0, you'll get something close to this, and by continuity, you probably can get something along those lines. Okay, so there is no general result about what happens with non-separable preferences, but what we can do is we can derive something similar to this, but with respect to the marginal utility of moving R resource in the future versus marginal utility of having R units of resources today. So we're going to utilize this, and also we're going to assume since we assume that there is a retirement in period t, that actually in the last period, it's very easy to show that the marginal utility in the last period is going to be exactly equal to 1 over u prime. So we have a result about the lifetime saving distortion, which is the difference between the marginal utility of consumption today and the expected discounted marginal utility of consumption in the terminal period. So that wedge you can sign. Okay? All right. So now let me talk about labor taxes, and let me actually skip some of the formal stuff, and let me talk more about the intuition. So let's first look at a static diamond or sides-like model of optimal taxes. So in a static model, your income tax is going to be determined by three terms, three forces. So one, which is driven by the elasticity of labor. So let's just think about this. The more elastic the labor is, the more costly is any given distortion. So the more elastic the labor is, there is a force that drives the labor or the income tax down. So the second force, which is something that Ilya talked today about, and it also shows up in not only in optimal taxation exercise, but in many, many other applications as well, is the tail ratio. The number of people above a given type divided by the number of people at your own type times your type theta. So it's 1 minus f of theta divided by theta times f of theta. So why do you need to have this? So think again about the static problem. So in the static problem, there is no particular need to distort anybody. You have lump sum taxes. If you want, you could use lump sum taxes. The only reason to have distortionary taxes is to help with incentives. How do I help with the incentives? Well, suppose I pick a person at any given type. By increasing the tax on that type, I have two effects. Well, the first effect is introducing a distortion. So his type is theta. There are f of theta number of people at that type. By introducing a higher type, I distort these guys. So it's costly for the planner. On the other hand, for everybody above that type, I make it less desirable for them to pretend to be this type. That's why you have this tail ratio that appears in essentially all of the incentive problems of this sort. The third part is the degree of the redistribution. How much a planner values people above some cutoff theta. Well, in this case, or if you want, you can look at the Olsen case as well, these people are not very valuable for the planner, these very high types. Their utility, the marginal utility of consumption is going to go to 0. So what Syeds and Diamond show that for the very, very high types, as theta goes to infinity, the tax on income for them converges to this number, related to the elasticity of substitution, the elasticity of labor income, times the tail ratio. Well, who knows what the tail ratio is, but in the data, it looks Pareto. Okay, so if this is Pareto, then this number is constant. So what you get is, for reasonable numbers of epsilon, and for reasonable estimation of the tail of the scale, you actually get pretty high numbers for the top incomes, on the order of magnitude from 50 to 80%. Okay, even if I change the elasticity here, make it lower, make it, it's not gonna that dramatically change the the results. So here I assume uniform Pareto weights. If you want, you can just forget about this part and just assume Olsen. Separate.
I mean, then the text would be a bit lower.
Yeah. But again, in the limit, the planner doesn't care about these guys, about the very high types. So that's why this term just drops off. Okay, so now let's look at the dynamic analog. So again, by writing down the problem recursively and thinking about this problem as a problem with two types, or two goods, the consumption and the resources that I move to the future over which I have indirect utility. I can, again, simple-mindedly solve a problem with two goods. The static Merlisson problem with two goods. And what do I get for the labor tax? Well, I get something similar and something different. So in a dynamic setting, the optimal labor tax, one thing I actually want to mention is the following. This is not a closed form solution by any means. This is just a rewritten first order condition of the optimal problem. So again, I can talk only about the forces that play out in the determination of the taxes, rather than about the moving from, say, the primitives. So the first force that is present both in dynamic and the static setting is, again, the elasticity. It's not really surprising. There is a cost of imposing a labor tax. The cost is higher than the higher is the elasticity. The second term looks like the tail ratio, but now this is a modified tail ratio. It has in this definition of f tilde also the promised utility, or the derivative of the promised utility. And the third term is also looks like the degree of redistribution. Let me just briefly mention what would happen also if you had persistent shocks. So if you had persistent shocks, there will be another term here, which makes the planner more distributionary, exactly the same way I described before. And here, instead of the unconditional probabilities, they're going to be conditional probabilities. Okay, so now let's look at this modified tail ratio. What does the dynamic add to the static model? It's again, so I want you to think again about us having two goods. One which is complementary with leisure, the other one which is not. Exactly as in that setting, what you want to do is you want to use the second good, or the future promises, to push down the labor income tax. So one can actually show that in dynamic settings, there is a force. So the 1 minus f of theta divided by theta of theta is going to be higher than this modified tail ratio, and the difference is going to be increasing in theta. So another way how to think about this is the following, is that in dynamic settings, when the utility is complementary with leisure, the planner wants to use dynamic incentives in addition to just pure labor tax or labor income tax to help provide incentives. Well, the question is how different this is. Let me, again, without going into the formal derivation, provide you the interesting results. So remember, if we look here for the very top guys, you get pretty high numbers for the optimal income tax. Here, in fact, we show that you don't want to tax, so the asymptotic tax on the high incomes goes to 0. So why is that? And the reason is the following. So suppose I have a person, so this is an IID case. Suppose I have a person who has a high income today, super rich guy. What he's going to be tomorrow? Well, he's going to be just an average guy tomorrow. Well, he's very valuable for me as a planner. He's super productive. So how can I entice him to work more? Well, I can entice him by lowering his labor tax. Okay? Or I can entice him by providing more stuff in the future, more resources in the future. But I just showed you that there is a wedge between the provision of resources in the future and provision of resources of today. So in other words, the amount of incentives I can gain from moving some resources to the future is relatively limited. So the only way to make these guys work very, very hard is to reduce their labor income tax, and in fact reduce it to zero. So the formal proof is actually somewhat significantly more involved, but I guess the gist of this is as follows.
So sorry, before I ask my question, so you're saying that it's not the reporting of their text, but it's the actual amount of effort that you're trying to do, or you're trying to get them.
It's the same thing, I guess. So so I want the person to reveal their true type. So I want a person to, and for that I'm going to allocate the person, consumption and effective labor.
I just want to know if it's driven by the elasticity.
No, it's separate. It's separate from elasticity. Elasticity or the force of elasticity is always there. The more elastic the labor is, the more costly it is to distort taxes. But in addition to that, so think about the static case for a second. So in the static case, if you had, say, linear taxes, for simplicity, then you would get a formula which will only have this in it with a little bit of modification. So this is a basic, deadweight loss of taxation. The more elastic labor is, the less you want to tax it. However, in the Merlisian settings, you have another thing. I mean, you can use lump sum taxes. Purely on non-distortionary taxes, they're fine. They are in the set of the taxes you can potentially use, but you don't want to use them because you can do better by introducing distortions. And these distortions are exactly introduced to make people reveal their types and provide, quote unquote, the right amount of effort.
I thought in the SIAS model, the type reporting was about taxation and avoidance, preventing people from avoiding paying taxes rather than.
It's the same thing. So you can think about the Merlisian problem in two ways. Actually, the static Merlisian problem is very easy to do. You can think either about this as a mechanism design problem, where you come to me on the planner, you report me your type, and given the type, I'm going to allocate your consumption and effective labor allocations. And of course, they have to be incentive compatible. So forget this problem for a second. Let's look at the classic public finance setting. The classic public finance setting, instead of that doesn't have to be any planner per se, there can be a nonlinear income tax. And that's what they characterize, a nonlinear income tax. And then one can show, actually very simply, the implementation. Any solution to the mechanism design problem can be implemented as a solution with a nonlinear income tax. The issue in dynamic setting, and then you'll see it tomorrow as well, is that you can't really do it. You have to be much more, it's much more involved problem. So you cannot just pose the taxes and get potentially the optimal problem. So it's much easier, and I think much better to do it, in fact, is to start with the mechanism design problem, where you find consumption and effective labor allocation over time, and then you find the taxes which implement them. So on one hand, it's in the static setting, so it's equivalent. In dynamic setting, it's slightly different, or it actually sometimes can be quite different, the correspondence between taxes and.
So is one way to think about this that there's a thinner tail of rich people in the static setup?
Exactly.
And then I guess my second question is, shouldn't you have the Frisch elasticity somewhere in the second? It's different than the first one. Because my understanding is the Frisch is something like you hold your utility constant, you change your wage in one period, and that's it, rather than you change your wage in the static model forever.
So you can, So this is actually a very good question, which I don't have a good answer. So which is, potentially, so here, another way how to write this formula, and that's exactly how science does in the static setting, is to write it in terms of elasticities. Various elasticities, and there can be something like this in dynamic setting, but I don't have a good answer for you on this. Okay. So what I have is just this essentially this thinning of the tail.
Would this zero top range result also hold in a static model with two goods?
Yeah, with the consumption labor being complements, consumption leisure being complements.
Because the way you described the second problem, you said you're kind of stuck in terms of intertemporal devices, and so all you can
I'm
do
not
is
really
really
stuck.
lower.
I'm not. No. I'm not quite stuck.
Quite
It's just
stuck, but-
there is an additional cost associated with it.
And so it sounded like fresh elasticity to me.
Yeah, a little bit.
Just because it's one period.
But it's fresh elasticity with respect to what? With respect to capital.
With respect to taxes, so effective wages.
I think it's much more complicated than this. So again, so I'm gonna have the same answer. So now back to the Domini's question. So yeah, so I think this is think about this literally as a problem with two goods. So one good which is complementary with leisure, the other good which is separable. So and you will get exactly the same. You'll get exactly the same result.
So then the idea that I can't expect so much money from the rich without the labor tax, but instead.
No. You do want to. It's slightly different. Is that you can extract everything you want from him, but I want to substitute some of the distortion to the good which has more, hit for the buck in terms of the incentives.
I think I was thinking more than
Yeah, but it's sorry. You can actually see this. So let me just for a second do this. So suppose you find the derivative with respect to c. It has an additional multiplier here. So basically, changing c helps you with the relaxed incentive computability constraint, while h is completely separable from this. So I guess you can think in terms of the the different taxes, the dead weight loss associated with different taxes, how much they help with incentives. Okay. All right. So what's the similarity and the difference with the static model? On one hand, they're quite similar. Once you rewrite the problem recursively using the dynamic envelope theorems, it's very similar to the static model with two goods. Good today plus properly defined indirect utility of moving some of the resource in the future. All right. On the other hand, this gives you much more nuanced understanding of how the incentives work in dynamic side. So let me maybe just summarize it somewhat maybe imprecisely, but quickly. So there are roughly two ways how to provide incentives. One, in the static setting, the only thing you can do is just hammer people with the labor income tax. Okay, that's the only thing that helps them provide incentives. In dynamic setting, you can also shift some of the incentives to the future by providing in the right way the promised utility. So in this particular setting that I described to you, so lowering the labor taxes is possible because I essentially substitute for the capital tax. I don't have to use that high of a labor tax. Maybe that's a better answer to Don's question. So instead of having a very high labor tax, I can just substitute a part of it with the capital tax. Okay, so let me just have first, the solution which is somewhat similar to Science's solution. Slightly different numbers, but so this is labor distortions. So this is the second period labor distortion, which is exactly the same as the static. The world ends, and this is the first period labor distortion. And you can see how you can just lower the labor distortion early in life at a cost of increasing the capital tax, and it goes down to zero higher on in the first period. So this is just an illustration. Let me now have a more serious empirical analysis. So I'm going to have a model which lasts for 20 periods. I'm going to have two years of life as being each period. I'm going to take agents from age 25 to age 65. And first what I want to do is to calibrate this model. The key parameter, as I have been talking about, as we have heard recently, is the skill distribution. And not only unconditional skill distribution that, for example, Science estimates, but also the conditional skill distribution, how your skills evolve over time. Well, you can say, well, isn't this the whole point of this problem, unobservable skills? How can you find out skills? Well, exactly what we're going to do is we're going to do exactly what Science did for the static framework. but for dynamic framework. We have the current system of taxation. What's the current system of taxation? It's very nicely summarized by NBR tax sim. So if we look at, say, PSID data, we can match to each person the marginal tax he has to pay. Well, if I put a little bit more structure in the problem, for example, if I assume some elasticity of labor supply, for example, being 0.5, we'll play around with different ones as well, then from the static first order condition, remember I have this quasi-linear utility function, u of c minus v of l, I can derive your skill. I observe your income, I observe your marginal tax, so I can just back out your skill. It's exactly what Sides does for the static setting. You can do it now for the dynamic setting. And now the interesting thing is I can calculate all kinds of conditional probabilities for how the skills evolve over lifetime. It's exactly what we do. So first thing I have to do is to estimate the initial distribution. What's the initial distribution? I'm going to take the people in PSID from age 25 to 30, and I'm going to just estimate density at different skills.
How are you defining a skill here? How are you defining a skill?
For the empirical thing? Oh, it's literally what comes out of this first order condition.
So what is it? So what does it mean to, you're going to try to estimate the initial skills, the distribution of them.
Yeah.
What is it that you're estimating?
I'm estimating theta, distribution of thetas.
So for periods in which you have data where you're backing it out, you don't have to explain what it is. But the initial distribution, you have to explain to us.
Yes, I'll have to. So I take basically 25 to 20. The initial distribution is I'll take everybody from 25 to 30 years old, and I just find the cross section.
What data are you looking at to estimate this?
So I'm looking at PSID data with a little bit exception because I need the fat tails. So like I also match it with CBO. So and I do two things. So I'll look at Y, the income you have, and I'll look at the marginal tax you pay. Okay, I can match every income with with the marginal tax due to NBR tax sim. Okay, I make a stance on the elasticity and exactly what. So this would exactly correspond to the skill in my model under my utility, under the assumption of my utility. I don't know whether I answered or not. Okay. So I mean, the only thing I have to do is, well, this will be super simple. The only thing is that PSID is very bad with this top skills. So I also match some of the CBO data to this. So just to get the Pareto tail. So I do this. Okay. So now what I do is the following. Then I split my sample into two groups. One which are 25 to 45-year-olds, and the other one is 45 to 65-year-olds. Okay, so and I assume that the transition probabilities within these two groups are the same for all ages, but different between these two groups. And I estimate just the whole probability, the whole conditional probabilities of moving, say from skill 100,000s to skill 200,000s if you are a young person to 45, and if you are an old person, if you are 45 to 65. Okay, if you don't like this, I can just check whether I get close to the results on the stochastic process for wages. It actually turns out to be quite similar to what Heathcote, Storsletten, and Violante estimate. Okay? All right. Okay, so what I'm going to do is the following. Actually, our calculation slightly changed compared to this since we're doing the revision. And but let me still give it to you. So what I'm going to do is I'm going to do a somewhat weird exercise. So I'll have to spend like 1 second to try to understand what exactly I'm doing. It's going to be really weird. I'm going to take two guys, one who makes $50,000 and the other one who makes $200,000. And then I'm going to suppose he makes $50,000. I'm going to estimate the whole profile of taxes for him from tomorrow on. And then again, say at suppose age 25, he was at 50K, and he'll face this tax. And then next period, suppose his realization of the of income is exactly, again, $50,000. What's going to be the schedule of the taxes he would be facing? And then again, and then again. I'm going to plot in five-year periods. And the same for a $200,000 type. And I'm cutting off at 300. Okay. So this is how the taxes look over lifetime. The first thing is a little bit weird. Actually, this changed in the recent computations because this used the initial distribution, which is not quite well done. So, but let me talk about what we see here. Well, there are two patterns we see. First of all, taxes increase with age. So why is that? It exactly comes back to that decomposition of different forces that I have. So the ability to provide incentives in the future allows me to drive labor tax down early in life. And the opportunities to drive them down become less and less and less as I reach retirement. Okay, that's the first thing. So both for 200,000 guys and for 50,000 guys, you have to be taxed lower early on. Well, there is the second effect. The taxes which a person who makes $200,000 pays for each age, but there are, I draw every 5 periods, but there is for every age, become significantly higher. So why is that? Well, there are two effects here. One effect is that stuff that we talked about the persistent types. The persistence in the income process or in the skill process makes the planner more redistributionary towards the lower types. Okay, so this is what helps a little bit with all these issues about the persistent shocks. If you lie in the past, how exactly I'm going to screen you out. Well, that's the first thing. The second thing, which is different, and certainly different from Science's work, is the conditional versus unconditional distributions. So obviously, the conditional distribution, unfortunately, I don't have them here, but I could have shown them to you. The conditional distribution of skills are very, very different with age, with income. So roughly, if you are a person who makes $50,000, you're probably very unlikely to ever make $1 million. While if you're a person who makes $200,000, it's a significantly higher probability, empirical probability, to make, say, $5 million. Okay, so these two effects are at play here. And what we see is that the conditional distribution of taxes shifts, and so depending on the previous history of incomes, and it shifts with age as well. So
those lines, is that saying that you basically should have a regressive tax on, so you're saying that
it's not quite regressive, marginal taxes still. And here?
Yeah.
Yeah. I mean, it depends.
That's for a particular individual. So someone's making $200,000.
So this is the guy. This is the tax, the labor income tax schedule for a guy who is at 59 years or 64. I forgot which one. 64, I think. At 64, made $200,000 for every single period in his life. He's a pretty lucky guy. Okay, so he made $200,000, and then he comes to period 65, and he knows that if he drops down to 50, that's going to be his marginal tax. If he is here, if he suddenly makes $3 million, his tax is actually going to go down quite significantly. Okay, and vice versa. We can look at the 64-year-old who makes 50K, and he's going to face a significantly lower tax. It's not quite regressive. Let's look at the second part. Remember, the labor income is not the only thing here. There is also capital income. For the capital income, you're just whacking those guys. I mean, again, sorry, let me say one. So let me just say one more thing. It's actually not even taxes; it's just the distortions. But you can think of them as quite incorrectly as the. So let me, yeah.
Well, I was just saying, are you assuming that? I know the classical assumption is that labor income can be distorted or hidden or whatever. But are you assuming that capital can?
Capital is absorbable.
So, but that's also. I mean, that's not very realistic.
It's not very realistic. I agree with you. I mean, I actually have. I'm going to talk a little bit about this stuff also tomorrow. But if you have also capital being unobserved, then this whole problem will actually, in fact, change. So, for example, you won't have inverse Euler equation. So this is assuming that the planner cannot observe your type, but the planner can observe your savings. Is this realistic or not? Probably it is. I mean, Ilya is almost as tall as Michael Jordan, when he was 10. But the fact that Michael Jordan, that he doesn't play basketball, doesn't really. Is it because his skill is low, or because he just doesn't want to play basketball? He chose to do economics. I mean, the reason I chose Ilya because he's the tallest, I think, person in the room. Maybe I know. Not as good as Michael Jordan. Maybe you do. So maybe now Michael Jordan is. So, but it's probably harder to determine this. Let me give you one example where it's certainly much harder to determine skill: disability, which is what I'm going to be talking tomorrow. So, disability is impossible to determine. Now, any one of us here, I know what's the system in Israel, but certainly in the U.S., any one of us here can fake disability, and nobody can ever determine otherwise.
Another question also in terms of the capital range. So, capital range of 0.2 would imply, for example,
The 20%.
if I interpret it directly as a tax, for example, on interest.
So, 20% tax on interest.
Would be 20%.
Okay. All right. So, so basically, the bottom line here is that what you want to do is especially for the high income guys, you want to substitute their labor income tax, labor income distortion, with the capital distortion, and it goes to 0. So here, I mean, if you look, you just almost don't tax at all the capital of this. A person in the U.S. who makes $100,000, I mean, this is not too poor. Only after 100,000, you get an increase. Let me do one more thing. So optimal distortion increases with age, continuous distribution of future shifts up. So let me do welfare gains. So here I'm going to follow Faria and Vernon, who did this exercise. I guess Manuel will do it. We'll do it tomorrow in this setup. So first I want to ask the following question: is if I look at utilitarian constraint optimum, is all of this, do we even have to bother about dynamic public finance, new dynamic public finance, and release on dynamic taxation? So if I have utilitarian constraint optimum, if I compare the constraint optimum with fully nonlinear distortions to the best linear age-dependent labor distortions. So I compare it to the linear taxes or linear distortions, which are age-dependent. If I compare it to the age-dependent labor distortions, I almost have no, I don't know, 0.6% is not that much of in terms of consumption, lifetime, every year in consumption is not that much. If I have age-independent labor distortion, I get 1.4%. So this is consistent and confirms the results of Faria and Vernon.
Did you compute also the welfare gain relative to the benchmark of the existing tax system?
At some point of time we did it, it's like huge, like 13%. I don't know, I forgot. Let me do slightly different size. Is this super surprising to me? Maybe. But what we know, for example, from like the calculations of Tuomala or Atkinson, is that if you have a utilitarian planner, that the welfare gain from linear taxes is not that huge, even the static models. So now let me compute the Rolson constraint optimum. So for the Rolson constraint optimum, I get that the optimal age-dependent labor distortion, age-independency, doesn't really matter, first of all, that much, but they give huge welfare gains. Okay, so the truth is probably somewhere in between. If you like utilitarian social planner, you probably say, well, it's probably not that much of an important endeavor to look in terms of the welfare gains at this optimal dynamic taxes. If you are a Rolson planner, it's huge. I mean, these numbers are very large. If you are in between, I guess we're in the US, we're moving more and more towards the Rolson planner. So maybe this is my forecast for the future. All right, I want to talk about, there's an implementation also proposed, but I'm going to skip it. So what I have done here is, and what I want to do is, and in general what I'm interested in is, I've worked for a while on all of these issues, and in the end, what I care about is about the policy implications. Can we use these models to think about how to design optimal tax policy, income policy, labor income tax, capital income tax? And I think this is a step towards this. It certainly uses the calibrate models. It uses realistic skill distributions. Estimates skill distribution, and does many other things. So it definitely brings us closer to this. So I view that our calibration to the US microdata is, I think, important to use as the feed into this problems. I identify driving forces behind optimal wedges. Again, in the classic public finance setup. So if you like static Merle solutions, if you have been taught SIADS or Diamond, then I think the way how to think about dynamic taxes as taxation with two goods is quite useful, because you will recognize many of the forces there, and dynamics will add, change, and sometimes dramatically change the pattern of the labor distortions. So I'm going to leave you with this. And yes, this is, after I think you see Emmanuel's and Ivan's paper tomorrow, hopefully it's going to convince you even more that we're much closer to the policy applications than from what it could have been derived, by just looking at this very theoretical exercise I have done yesterday, for example. Ilya. The what?
Gaming of the system, which in some sense, dynamic, I mean, part of it is what is one period. So dynamic, it could be every day you pay tax depending on what you made today and on the history. And of course, the gaming is that the employer doesn't pay every day. So and then of course now you pay every year, but if you do it more dynamic system, then you could gain when you get paid.
Sure.
Go around this. So do you have any idea of?
I mean, look. So I think it's. I mean, yes and no. So I mean, what I like about this approach, I think in general, that it starts with informational friction. So, for example, let me add to the informational friction of an observable skills today is also another friction. Suppose I can hide my income and move from today to tomorrow. This can be done, for example, with hidden savings. Something which I'm going to be very briefly touch upon tomorrow. So that's another condition which makes all of the incentive compatibility constraints in main dimension stronger, more difficult to satisfy. So to answer this question, what I would say is that you tell me what frictions are important, and I'll give you the optimal solution. Hopefully, I can give you for now for this, but I have thought very carefully about this in simpler models. Like when I'm going to be talking about disability insurance. So in disability insurance, I calculated a variety of the possible ways to game the system. Like there's an audit, there's some probability of the audit succeeding, not succeeding, if you hide your savings, et cetera, et cetera. So here I don't have this yet.